Hey everyone, welcome to today's lesson on waves. I think this is kind of a fundamental topic in physics as it helps to explain how energy can be transferred from one spot to another. It helps to explain a lot of different phenomena that we see in our natural world. Probably have a lot of experience with waves, although maybe not quite in the sense that we're going to see here today, but especially in several of your different math classes, you will have a fair amount of experience with a lot of what we're going to cover here today, having to do with one particular type of wave, which we'll be talking about momentarily. Now, to start, a wave is a vibratory disturbance that moves or propagates through a medium, and a medium is just a body of matter. This might be water, it might be a wall, it might be a vacuum, it could be a field. But every wave at its source has some type of particle. Could be a particle of the medium, could be an electron as part of the body of matter that's vibrating or oscillating about some average position. And as I was saying, waves describe how energy can be transferred from one place to another. And this is done by repeated small vibrations of a medium. If you think of all the matter, atoms in a body of matter, if they're kind of vibrating or shifting or moving about an average position of that body of matter, it's going to produce a wave. This could also be done by repeated small changes in the strength of a field as well. Now, mechanical waves, these would be, for example, sound and water waves require a material medium in order to actually occur. There's my guy there. Lost that for a second. Sound and water is not going to move without a material medium or some type of matter to move the energy. For example, sound doesn't travel through the vacuum of space. Water waves aren't going to propagate unless we have water for those waves of energy to move through. But electromagnetic waves, like visible light and radio waves, can travel through a vacuum, which is a region of empty space. So electromagnetic waves from the sun are able to propagate and move through a vacuum to make it to Earth, to do a variety of different things depending on the type of wave that is being transmitted. Now, only energy is transferred. There's no actual matter that's being moved from the source. Only energy is being transferred from the source to another object. Now, waves are classified as either pulses or periodic waves. And we'll take a look at the difference between both of those. Now, a pulse is a single short disturbance that moves from one position to another in a field or medium. For example, here, A is an example of a pulse. We see this hand kind of flick the rope, and we see this pulse move down the rope. Then it hits the end here where the rope or the spring is hooked onto. Now, the speed of the pulse will depend on the properties and type of the medium. Now, if a pulse reaches an interface or boundary of a different medium, Could be, let's say, sound moving through air and then reaching water. Maybe you're dunking your head underwater and try to listen to somebody say something that's not in the water. This could kind of be an example of that. Part of the pulse is going to be transmitted through the medium. Part is going to be absorbed, and part is reflected back to the source. So if you think of a person being, let's draw that a little bit better here, underneath the water, and somebody standing on top trying to talk to them underneath, part of these waves here are going to be transmitted through the water to the person. Some are going to be absorbed by the water, and some are going to be reflected back towards the person itself. The reflection is the rebounding of a pulse or wave as it strikes a barrier. And you probably have more experience with this than you think. Ever been in an empty room? You'll get a stronger sense of this, but ceiling tiles, drapes, carpeting. Have you ever been in a room that doesn't have carpet in it? It's almost like things sound a little bit louder or maybe more echoey, because these ceiling tiles, drapes, and carpeting work to absorb some of the energy of that sound wave that strikes it. When you have sound waves that are striking, let's say, a curtain, part of that wave gets absorbed, and the reflected wave has less energy than the original. Now, these pulses are different than a periodic wave. A periodic wave is a series of regularly repeated disturbances of a field or medium. Regularly repeated pulses. So I'll show you an example of that. I'm going to keep this fixed here, and I'm going to give one little pulse. There's a lot of different things we can change here. I'll kind of leave this as is. And we can give a pulse, which is just a single short disturbance. And we see that wave kind of propagate down, and you can see here that it gets reflected backwards. That's because we have the wave fixed here on this clamp. Newton's third law says for every action there's an equal and opposite reaction. So the pulse that we see traveling in the positive direction from equilibrium gets reflected back, inverted, and travels underneath the line of equilibrium. And that's because this rope is attached to a fixed body. So the pulse that we apply here is completely reflected backwards. None of the wave's energy here is being, I guess it's kind of being dampened. But if we take off all the dampening, we can see it is completely being reflected backwards. None of it's being absorbed. A couple different types of wave motion. A longitudinal wave is a wave in which the motion of the vibratory disturbance is parallel to the propagation or travel of the wave through the medium. And the best example of this is sound waves. Well, sound waves, or you can, if you remember back to earth science, P waves from earthquakes are examples of longitudinal waves, or compression waves in a spring. If you think of a slinky and you kind of compress it or stretch it and let it go, it kind of moves back and forth. But the direction in which you pull the slinky is the direction in which the wave is moving. So the particle motion is in the same direction as the movement of the wave, or the direction of propagation, meaning that they are parallel to each other. A transverse wave is a little bit different. In this case, the motion of the vibratory disturbance is perpendicular to the direction of travel of the wave. And in earthquakes, these are our S waves, or what we'll focus on here are electromagnetic waves. Now, if we were to, in that example we were just looking at with a rope attached to a wall, if we move the rope up and down, representing the motion of the particle, the wave's going to move left and right. And these form right angles, so they're perpendicular to each other. And this is different than what we see with longitudinal waves here. Now, some characteristics of periodic waves. Now, this is mostly what we're going to be focusing on. The few different characteristics that we need to be familiar with. And certain characteristics that we'll discuss here are going to distinguish one wave from another similar wave. And these characteristics include frequency, period, amplitude, phase, wavelength, and speed. Now, a complete series of changes as a wave passes one point in a medium is known as a cycle. And if you remember from, I forget which math it would be in, but looking at different parts of sine waves or cosine waves, I guess that would be trig. We have something kind of like that, where the top here represents 90, 180, 270, and 360 degrees. And from 0 to 360 is essentially one cycle. The frequency, represented by f of a wave, is the number of cycles or complete vibrations experienced at each point per unit time. And we call a frequency of 1 cycle per second 1 hertz. And there's a little graphic here to kind of show 3 hertz. So the time here, the t, the period, 1 second from red line to red line, we have 3 hertz in the red, meaning we have 3 complete waves, 1, 2, 3, happening in 1 second for a frequency of 3 hertz. 6 hertz, we would have 6, 3, 4, 5, 6, and so on with 12 hertz. Now, the frequency of a sound wave is going to determine the sound wave's pitch. So a 12 hertz frequency is going to have a higher pitch than a 3 hertz frequency. And human ears can detect sound frequencies in the range of 20 to 20,000 hertz. The frequency of a light wave determines the color of the wave. And human eyes can detect light frequencies, which are different than sound waves. 3.84 times 10 to the 14th to 7.69 times 10 to the 14th hertz. And that is the range of the visible spectrum on the electromagnetic spectrum, which we get to later in this unit. So we have a listener here with a sound source. And we're going to kind of play around with a couple things here. We're going to be the listener, and I'm going to enable the audio here. We'll see how this works. Right now there's no sound coming out because we have no frequency. So if I change the frequency, we still don't have any sound, and that's because we don't have any amplitude. Now the amplitude, I'm going to change this here. We'll start off kind of small. We can see a wave propagating from the source. We can't really hear anything too well. So let's see what happens if we change the frequency. We see, now we got a little sound here, but we see a change in the wave. And these light and dark colors here are our condensations and rarefactions, which we're going to talk about in a second. But this is the disturbance of the medium, where matter is being compressed and expanded as the sound wave moves through whatever this medium is here, probably air. Now the frequency, if we change this to a higher frequency, we see a change in the wave, and we see hear a much higher pitch. So the difference in the waves here, these are much finer. Whereas if we lower it, these are much thicker and a lot lower pitch. A little bit harder to hear. So we see the difference in the compression of the matter through the wave from a lower frequency to a higher frequency. And we'll come back to that. So the period of the wave is the time that's required for one complete vibration to pass a given point in the medium. And the period of a periodic wave is inversely proportional to the frequency of the wave, and that's given by the equation of 1 over the frequency. That's how we'll find the period of a wave. Where t, our period, is in seconds, and frequency is in hertz or per second. The amplitude of a mechanical wave is the maximum displacement of a particle of that medium, let's say air. The maximum displacement of a particle in air from its rest or its equilibrium position. Kind of, you think of an air molecule sitting wherever it was, it gets displaced by some type of mechanical wave moving through it. However far it gets displaced, that's the amplitude of the wave. Now in a transverse wave, the position of maximum displacement of one of those particles in the positive, let's say upward direction, is what we call a crest. So it's the high point on this transverse wave right to the right. The position of maximum displacement downwards, or in the negative direction, is called a trough. The greater the amplitude, the higher the crest and the lower the trough. So if we were to have a greater amplitude, this might look something like that. Higher crest and a higher or a lower trough. Now in a longitudinal wave, which we were just looking at with the sound waves, the periodic displacement of particles of the medium produce regions of maximum compressions, which are the dark lines here. Maximum compressions that we call condensations, that are going to alternate with these regions of maximum expansion, which we call rarefactions. Now changing the amplitude, I'm going to enable the audio here. If we change the amplitude, we see 1 a much louder sound. And these lines got darker, indicating a greater amplitude, indicating a greater displacement of a particle from its equilibrium position. Now the frequency, if we lower the frequency down, we see a change in our points of maximum expansion and compression, which are going to indicate our wavelength. The amplitude of a wave is related to the amount of energy that it's transmitting. So the greater the amplitude of a light wave, the brighter the light intensity. And I'm hearing this buzzing here. I'm going to have to turn off the audio. And the greater the amplitude of a sound wave, as we just saw on the simulator there, the louder the sound. The phase of a wave, this one we might be a little more familiar with, is where points on successive wave cycles of a periodic wave are displaced from their rest position by the same amount in the same direction. For example, given the wave here on the right, and transverse wave here on the right, we have several different points here. We can count, so from A to F, we have one complete cycle. And then we have a second cycle from F over to our point here. Now, points A and F are 360 degrees apart. B, G, D, and I, I'll start with B and G. B and G are at successive points on two different wave cycles. So those are 360 degrees apart, as well as D and I. D is displaced. Remember, this is 90 degrees. And I here is the same thing, displaced 90 degrees from the beginning of that cycle. E here is at 180. Down at the bottom here is 270. And back to the beginning is 360. E and F, which I kind of mangled up here a little bit. E, can't really see F too well in there. I'm going to just erase this here. E and F are 180 degrees apart. They are out of phase. E's at 180 and F is 180 degrees away, or at 360. So the difference here is 180 degrees. They're on the same cycle, but they're 180 degrees apart, so they are considered out of phase. Now the wavelength of a wave is the distance between any two successive points in phase with one another in a periodic wave. Wavelength is represented by the Greek symbol lambda, and it's usually measured in units of length, like meters, or oftentimes nanometers. Now we can measure wavelength on a transverse wave by measuring the distance between successive crests or troughs. And it'll be similar for longitudinal waves by measuring between successive condensations and rarefactions. I'm going to come back here and I'm going to change this to oscillating. This is going to look kind of weird, which we'll get into this a little bit later with standing waves. But I'm going to put no end on here. This is kind of free to flow because this is going to give us a nice looking periodic wave with a particle that is oscillating about its average position constantly. Now we can change the amplitude of this wave, which is going to change the highest points and the lowest points. So if we were to decrease this down, we see a much smaller wave, if this were a light wave, brightness would be very low. If we were to increase the amplitude, the brightness would get greater. Or we have taller troughs, or taller crests and lower troughs. Frequency, looks like we set up about, we got almost 2 hertz, looks like 1.5 hertz here. I'm going to change this down to 1. Try and keep it simple here. So we have 1 hertz here, 1 complete wave in this cycle, 1 per second. There's no dampening on here, meaning that there is no energy being lost. Nothing's being absorbed. Nothing's being reflected. If we change the frequency, this is going to go from 1 hertz. If we increase it, we're going to see a lot more cycles being completed in this particular amount of time. So these are going to get much shorter and closer together. In this case, we have 3 successive waves being formed in this 1 second time frame here. We can lower the amplitude of that, but keep the frequency the same. We still have the same amount of cycles being completed. There's just less amplitude or change from the average position happening with each successive wave. Now, the speed of the wave is equal to the product of the wave's frequency and wavelength, where V equals F lambda, where F, or frequency, measured in hertz, lambda is our frequency. Lambda equals wavelength, usually measured in meters, and V is the speed of the wave, usually measured in meters per second. Now, the speed of the wave will depend on the type of the wave and the medium through which it's traveling. I'm going to do a couple quick examples here. Hopefully this won't take me too long. And there are spots to write your answers in down here. I'm going to, for the sake of time, I'm going to write them next to my question here. Then we're given, take a second to think about this. What type of wave is this? It is a transverse wave. And we're given a couple different parameters here and several different points on the wave. And this is showing a segment of a periodic wave in a rope traveling to the right to point G. So the direction of travel, or velocity, is to the right. Now, the type of wave that's represented here, we said, was a transverse wave. The amplitude, the change in a particle from its equilibrium position, or from a crest to a trough. In this case, we're given from crest to trough is 2.4, but the amplitude is going to be half that. The average displacement is from equilibrium, or this line here, up to the point, which is a positive 1.2. This would be like a negative 1.2. So the amplitude of the wave will be 1.2 meters. The wavelength of the wave, which is measured from successive points, showing 1 complete cycle. So that could be from B to here, be from A to E. So we have, I'm going to go from the start here to E. And this gives us 1 whole wave. But then we're still left with this region here. Remember, this whole thing is 360, so at this point, this is 180 degrees. So this part here is 180 degrees. That's a half a wave. So what we're looking at here is 1.5 wavelengths. And that would give us a wavelength of 4 meters. If the total section there is 6. One wave would be 4 and half of another would be 2 for a total of 6. Now if the frequency is 2 hertz, what is the period of this wave? Well, to find frequency, the frequency of the wave, let's see here. If that is 2 hertz, we have, let me find that. If the frequency of the wave is 2 hertz, what is the period? Well, to find the period of the wave, that's T equals 1 over F, which is 1 over 2, which would be half a second. Determine the speed of the wave. Speed is determined by the product of frequency times the wavelength. The frequency we know is 2 hertz times a wavelength of 4 meters, which gives us a speed of 8 meters per second. I'm looking for 2 points on the wave that are in phase together. So 2 points that are on successive spots on the wave that are equidistant from each other. This would be C and F. C and F here are 360 degrees separated from each other. We could call this 90, or maybe this is 135 degrees, and this would also be 135, or we could call that, no, we'll keep it at 135 degrees from that starting point of the wave. So those would be in phase with each other. B and D are out of phase with each other by 180 degrees. So we have B up here at 90 degrees and D down here at 270 degrees. So the difference there is 180 degrees. So those 2 points are 180 degrees out of phase with each other. So we said that was C and F. Now immediately after the wave moves through point G, will point B move up, down, left, or right? Well, this is the direction particle motion as the wave travels to the right. So after the wave moves through point G, point B is going to move down as it follows along that wave. We'll do lots of practice with this. I know I kind of threw a lot at you guys there, but there's a lot to take in here and a lot to do. If you have any questions, write them down and make sure you ask them and get an answer found for them. Hope you guys have a great day.